All right, here we go. We define the maximum and minimum values of the objective function. There's your objective function. That's what we have to maximize and minimize by plugging in some points. And for what values of x and y they occur subject to the following constraints. We have these constraints on x and y. X plus y can't be greater than 8. That creates this line with a y-intercept of 8 and an x-intercept of 8. And we should probably be a little bit more careful when we're graphing these, so that, because we want to find some intersection points. Then we have 2x minus y is less than or equal to 5. This one we should probably put in slope-intercept form because the x-intercept would be 5/2. All right, so we'll minus the 2x over, divide by -1, so that means y is greater than or equal to 2x minus 5. We have a y-intercept of -5, and then a slope of 2. So up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. And now that I've intersected that line, that's probably good enough. As a matter of fact, I have this little tool. That makes it handy. And then we have x is greater than or equal to 0 and y is greater than or equal to 0. So that puts us in the first quadrant. So there's the y equals 0. There's the x equals 0. And so we're in this area right here. Oh, wait. I just know that from last period. I should explain that. Like, hey, just throw it in that area. You weren't here 4th period? Come on. We are less than this one. So less than the first one, right here. And we are greater than the other one, and we have to stay in the first quadrant. So there you go. There you go. Now that area is called the feasible region. That's where, according to the constraints, that's the values that we can pull from. That's the points we can pull from. Fortunately, the minimums and maximums happen at the vertices of the feasible region. So we have 1, 2, 3. We have 4 possibilities for mins and maxes. So up there at the top, we have 0, 8. We have 0, 0. We have the x-intercept of the second graph, which ends up being 5/2. So 5/2, 0. And then we have that intersection point. It's the intersection of these two lines right here, and this is pretty much set up to find the simultaneous solution to solve the system of equations. We can just add. So 3x is equal to, and I'll put equal to because we're looking for a specific point, is equal to 13, so x is 13/3. Well, now I have to get the y. Well, if I pick either one of these, I can have 13/3 plus y has to be equal to 8. So y is 24/3 minus 13/3, which is 11/3. So the other point is kind of ugly, 13/3, 11/3. Now the graph tells me that I'm finding the intersection of those two lines, but the graph isn't accurate enough to give that as an answer, so we'll have to do what we've been doing the whole chapter. There's your 4 points. Now we're going to plug those 4 points into the objective function, find out which gives us the biggest value, which one gives us the smallest value. 8 times 3 is 24, 0 for the x. 0, 0 gives us 0. 5/2 plus 0, well, that's just 5/2. And then we got to do a little bit of work on this one. It's going to be 13/3 plus 3 times 11/3 is 11. So that's 13/3 plus 33/3. So 46/3. That's the value that we get in the objective function on the last point. Well, this is 15 1/3. And that falls in between these two right here. So now we have to answer the question. Minimum, I just need minimum, M-I-N. Minimum of 0 at 0, 0, and a maximum of 24. That's the maximum value at 0, 8. So there's your minimum values and where they occur. And that's the instructions ask for both of those. All that information. Go ahead.
Okay, so like the 5 halves, you said it was in between the 24 and the 0. Like, what do you mean by that? I guess?
Well, that's 2.5.
Yeah.
That's in between 0 and 24. That's not a min or max.
Oh, okay. I see.
So you're always going to find all people only choose lowest.
Anything else? A garden center grows only junipers and azaleas in a greenhouse that holds up to 3,000 shrubs. Well, if it holds 3,000, and we go, let's go with what's first? Junipers. Junipers, azaleas. So x plus y has to be less than or equal to 3,000 because the greenhouse won't hold any more than that. Due to labor costs, the number of azaleas grown must be less than or equal to 1,200. So, okay, hold on. We got number of azaleas, y, and literally says must be less than or equal to 1,200 plus 3 times azalea or junipers, and that's the x. The market demands for azaleas is at least twice that of junipers. So y is at least. So greater than or equal to 2 times x, because it's twice that. The y is twice the x. So to even it out, to make it equal, I'd have to multiply 2 times the x. Well, the y could be more than that, more than twice. So there's your third inequality. Now to speed things up a little bit, I already graphed them. I'll talk about it a little bit. The blue, here's the blue, goes from 3,000 to 3,000. This is in slope-intercept form where this is the red. We got 1,200 plus 3x, so the y-intercept's 1,200. Up 1, 2, 3 spaces and over 1. Up 1, 2, 3 spaces and over 1. And you're not going up 3 and over 1, but you're going up a multiple of 3 and over a multiple of 1. That's okay. It doesn't have to be, if you're going from 1,750 to 2,000, you don't have to count up 3 and over 1. You can go 3 spaces, 1 space, it's the same thing. And then we have an intercept of 0 and a slope of 2. So up 2 over 1, up 2 over 1. So this is the green. Sketch a graph of the region. That's exactly what we did. Determined by the constraints from part A to find how many of each plant the company should grow to maximize the profit. I never did write the profit function. So here's the profit, XY. It's on that last sentence if I remember right. The center makes a profit of $2 per juniper, so that ends up being 2x, and $1.50 for azaleas. First things first, I'm the realist. X plus y is less than or equal to 3,000, that's the blue. So we're less than on this one. If I put that in slope-intercept form, I wouldn't have to divide by a negative. It's the slope-intercept form that tells you above or below. This one's already in slope-intercept form. It's the red, so we're less than the red. And that's in slope-intercept form, so we're above the green. So the feasible region is right inside here. Now we got to get our vertices of that feasible region. First of all, 0, 0. I don't think you're going to make much of a profit if you sell nothing. That's probably not going to be the answer. It would appear that if I were to solve the blue and the green, they cross at 1,000, 2,000. Well, that's a pretty easy check. 1,000, 2,000. If I plug 1,000, 2,000 into, I need the blue and the green. 1,000 plus 2,000 is 3,000. 2,000 times 1,000 is 2,000. So that's actually the point. Now we got to check that because when you graph, sometimes it could look like it crosses at a nice point, but maybe it doesn't. It may not, especially if we're going by 50s all the way up to 3,000. Could be very inaccurate. The other point is between the red and the blue. I have no idea what that point is. I actually don't even remember from 4th period. That doesn't help me out. I need red and blue. These two right here. Is that it? Yeah, the red and the blue. If I minus the 3x over, x plus y is equal to 3,000, and I have negative 3x plus y is equal to 1,200, those are already, that's ready to subtract, right? Because I get rid of the y's. So 4x is equal to 1,800. So x is 450. So that's the x. I need to subtract that from 3,000. I don't think I need a calculator for that, but I'll give it a try here. 2550, right?
Yep.
So the other point is 450, 2550. Now we have a fourth one if I remember right. Yep, it's right here. Now that's the y-intercept of the red. That's 1,200. So 0, 1,200. Now we got to find out which one of these maximizes the profit. And here's the profit function right there. Now, we know that one right away. Not going to get much if you don't sell anything. 2,000, 2 times 1,000, plus 1.5 times 2,000. 5,000. So we get 5,000. I should have left a little room. I didn't do that. 5,000 there. 2 times 450 plus 2,550 times 1.5. 4,725. So we're just short, right? So far 1,000, 2,000 makes it. And now I just need 1.5 times 1,200. I think that's 1,800. Yep. 1.5 times 1,200. Yep, 1,800. So we should sell, here's the maximum right there. We got to answer the question though. 1,000 X's, and I made X junipers. And I made 2,000 azaleas. If one of your problems, if the answer would have been this right here, I get that that's not a very good business model to not offer any of the others. Don't do that if you own a business. I get it. But we're just going off the pure math, not what would make a good business model, okay? You can talk about that in your business classes. I get it. If 0 to 1,200 gave me the maximum profit, as a good business person, I wouldn't do that. I get that. So don't make that argument with me. I already get it. I'm already there. All right? Find the partial fraction decomposition. So let's review a little bit. And I picked this one because it's so easy to forget to divide. So if the powers are the same, you have to divide. And the bad part about this is you could do the process without ever dividing and get values, and they'll be wrong. The answer will be wrong. So that's kind of a dangerous situation, I guess. We like to have something tell us that we're doing something wrong, and it just wouldn't be there. So we have to do the division. It's usually only about 1 or maybe 2 steps. So we have 3x squared minus 6x minus 9. And we're subtracting, so that's 6x minus 2. Not plus, woo. There we go. Well, now it's 3 plus 6x minus 2 over x minus 3 x plus 1. Now we're doing the decomposition on the fractional part. We'll just remember to bring the 3 with us eventually. Well, now that's supposed to be a over x minus 3 plus another number b over x plus 1. And now we need to find the a and the b. Let's multiply the top and bottom by x minus 1 there, top and bottom by x minus 3 there. Now we have 6x minus 2 equals a times x plus 1 plus b times x minus 3. When it's fairly simple, I don't distribute the a's and the b's. I just let x equal negative 1, but you sure can. you can do it with distributing and doing the same coefficients and all that. It'll work. But I think this is a little more simple. Negative 6 minus 2, that's negative 8, is negative 4b. B is 2. I didn't leave enough room, really. Let x equal 3. 18 minus 2 is 16, equals 4a. 3 plus 1. A is 4. So now we're ready to write the answer. Don't forget to bring the 3 with it. Remember that we divided. We have the 3 plus. Don't forget to tack that on. We have a, which end up being 4 over x minus 3 plus 2 over x plus 1. Any questions? And then the last one I want to show you today is just a review of factor by grouping more than anything. When we have 4 terms, there's a good chance it's factored by grouping. And remember, they're in the same ratio, 1 to 3 and 1 to 3. If they're in the same ratio, big time factor by grouping. All right, take out an x squared, x plus 3. Take out a 3, x plus 3. The x squared and the 3 come back together, and the x plus 3's come back together. Well, now we want this to equal ax plus b over the quadratic over the x squared plus 3. Remember that the top has to be 1 power less than the bottom. So if the bottom's an x squared, you got to make the top linear. Plus c over x plus 3. Well, now we need negative x squared plus 2x plus 3 to equal ax plus b times x plus 3 plus c times x squared plus 3. Need to extend this a little bit, not that much. That comes from the common denominator, right? Multiplying this times x plus 3, that times x squared plus 3. All right, here we go. Ax squared, first outside, plus 3ax inside, plus bx last, plus 3b plus cx squared plus 3c. Well, now a plus c is equal to negative 1. There's your x squareds. Your x's are 3a plus b. 3a plus b, and that's equal to 2. And then 3b plus 3c is equal to 3. That's your constants. That's the ones without x's, of course. Well, I think we could do this by hand, but I'm going to allow calculators on this part. So let's throw it into a calculator and let it spit out the answers for us. Clear. Let's go into matrix. We're going to edit A, and we're going to have a 3 by 4. This is really, remember you have an A, a B, and a C column. So this is really 4 columns, not just 3. 1, 0, negative 1. 1, no, not 1, 3. 3, 1, 0, 2. Don't forget to plug in the zeros. Remember, if an A, B, or C is missing, you got to plug a 0 in for that. There's the 2. Oh, wait a minute. I'm all messed up. Double check that. 1, 0, negative 1. Oh, what? I must have got off track somehow. Okay, here we go. 1, 0, 1, negative 1. There we go. 3, 1, 0, 2, and 0, 3, 3, 3. I think I already have. Oh, we go into matrix, math over there. One more, RREF, matrix A. 0, 2, negative 1. So the A is 0. I have 2 and negative 1. 2 over x squared plus 3 minus 1 over x plus 3. Any questions? Very good.